Welcome to video 6.1b, where we will continue our discussion of collision theory and rates of reaction. In terms of remembering your prior knowledge, the kinetic molecular theory is going to be helpful in understanding that higher higher temperature results in faster moving particles, Maxwell-Boltzmann distribution curves, collision theory of reactions, the fact that most reactions require a collision with the proper orientation of the particles and with enough energy to overcome the activation energy barrier. And those are going to be helpful things to remember today. It'll also be helpful to remember how we measure reaction rates. It's not the case that we typically just time a reaction and see which one is faster. We actually want to find the actual rate. So typically this is done finding some concentration of something over time. Maybe this is concentration of a product. And we take the tangent at a particular point, typically the earlier the better, and the slope of that line is the rate. And that is the key to understanding how to measure rates of reaction. And then Maxwell-Boltzmann distribution curves are going to be helpful if we think about activation energy. If this is the activation energy for a reaction where the molecules need to be traveling at least this speed or higher in order to have enough energy to overcome the activation energy barrier. Think about how different temperatures impact the number of particles that have the activation energy. It's going to be something we're going to talk about today. So the big idea is actually the same as 6.1a. The greater the probability that molecules will collide with sufficient energy and proper orientation, the higher the rate of reaction. Our focus today is on a few new syllabus statements, but I've got one highlighted in red here. Explanation of the effects of temperature, pressure, concentration, and particle size on the rate of reaction. Pressure and concentration are kind of related, and you'll see that. And then this relates to concentration changes in a reaction can be followed indirectly by monitoring changes in mass, volume, and color, and you will have done some of that in our exploratory lab. Construction of Maxwell-Boltzmann distribution energy distribution curves to account for the probability of successful collisions and factors affecting these, including the effect of a catalyst. Although recall that a catalyst we discussed in 6.1a with an alternate pathway that lowered the activation energy barrier. So there are some factors that affect reaction rate. Some of these you may have studied previously. We'll get into more detail in 6.1b today, and even a little bit more detail in 16, the higher level material. Temperature, concentration, particle size, which is sometimes called surface area, pressure, and the presence of a catalyst, which again we've already talked about. So we're going to focus on these four items, these four factors. So how does temperature affect reaction rate? Well, I hinted at this in the opening related to accessing your prior knowledge. So I have two Maxwell-Boltzmann distribution curves, one at 300 Kelvin and one at 310 Kelvin. The 310 Kelvin has a lower peak, but the peak is at a higher kinetic energy. And if I look at the number of particles under the curve that have at least the equivalent or higher energy compared to the activation energy, when I have a higher temperature, I have more particles that have an energy greater than the activation energy. So if I increase the temperature, the particles move faster. And so if I increase the temperature, I increase the frequency of the collisions. That's thing number one. But thing number two is I increase the probability that the energy of the particles in the collision will have an energy greater than the activation energy. So increasing the temperature actually is a twofold reason for increasing the rate. Number one, the particles move faster, and so that increases the frequency of the collisions. Particles moving faster will collide more frequently. And if I have more frequent collisions, the number of successful collisions will also increase in terms of the frequency of the successful collisions. But Not only that, but because I have a higher temperature, I have a higher probability that the energy will be greater than the activation energy for every collision. So let's think of a scenario where 10% of the collisions have enough energy. If I increase the frequency of the collisions, even if it's still only 10% of the collisions are successful, if I have more collisions overall per unit time, I'm still going to have a faster rate. But increasing the probability not only makes there have a higher frequency of collisions of all kinds, but maybe it makes them have 15% of the collisions now have enough activation energy to overcome the energy barrier. So not only do I have more collisions in a unit of time, but a greater percentage of those collisions are now successful. Increasing temperature is a twofold double whammy, so to speak, for increasing the rate of reaction. Now, I wrote this on the previous slide. This is a bit of a summary written with, say, nicer text than my scratchy writing. Increasing the temperature increases the rate of reaction because the particles are moving faster, thus the frequency of collisions increases. But particles have more energy, so the proportion of particles that have values for kinetic energy greater than the activation energy increases. So this is an increase in the frequency of successful collisions. Let's make this graphical. These are successful collisions at 300 Kelvin. Okay, at 310 Kelvin, I'm going to have more frequency of collisions, first of all, but I'm also going to have a greater percentage of those collisions will be successful. So I'm increasing the frequency of successful collisions in two ways. One, by having more collisions in general per unit time, and the other is by increasing the percentage or proportion of the particles that actually have enough kinetic energy to overcome the activation energy barrier. This is a key. Now our next factor is concentration. On the right hand side we have low concentration, on the left hand side we have high concentration, relative to each other. Low concentration, in order for the blue and the green particle, whatever they are, to react, they must collide. If there is a higher concentration, then the frequency of collisions will be higher. So increasing the concentration increases the frequency of collisions. I want to emphasize the word frequency here. It doesn't increase the number of collisions, it increases the frequency of collisions, because the number of collisions is time dependent. Wait an hour, you will have more collisions than if you waited a minute, no matter how slow you were going. So higher concentration increases the frequency of collisions. If I have a greater number of collisions per unit time, then I will have a greater rate because the number of successful collisions per unit time will also go up. But this does not have the same effect as temperature. This simply increases the frequency of collisions. It does not increase the frequency of... It does not increase the percentage of collisions that will be successful. But if 10% of every collision, if 10% of all the collisions are successful, if I have more collisions per unit time, I'll have more successful collisions per unit time. So the rate increases. Increasing concentration for aqueous or gas phase reactions will increase the frequency of collisions and thus will increase the rate of reaction. Again, this is a restatement of what we just talked about with slightly nicer print. Particle size, which is sometimes called surface area. If I have large particles versus small particles, I have increased the surface area where collisions can take place, collisions on the surface of the particles. If I have more surface area, I have more frequency of collisions, a higher frequency of collisions. You're thinking, all right, well, let's talk about this from a mathematical perspective. If I say that this has a length of 2 and a width of 2, and we're going to use sort of a two-dimensional space here. That means that this has an area, and I'm going to put area in quotes, of 8, because what I'm really talking about is the perimeter, because this is a two-dimensional space here. 2 plus 2 plus 2 plus 2. So there's an area, quote, 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 area of 8. But if each of these is one of these squares, that means that each of these squares has an area equal to 4. So 1, 2, 3, 4. And I have 4 of those particles now. So 4 times 4 is 16. So by making smaller particles, I increase the surface area. So by decreasing the particle size, I increase the rate. Or by increasing the surface area, I increase the rate. Sometimes IB will ask related to particle size, sometimes maybe related to surface area, and I think you need to be ready to answer both. But recall that particle size is inversely related, whereas surface area is directly related. And again, this is because of the frequency of collisions. There's a higher frequency of collisions when I have more surface area, when I have decreased the particle size. For reactions that involve substances and phases that do not mix, such as a solid in a liquid or a liquid in a gas, the decrease in particle size will increase the frequency of collisions, and the decrease in particle size relates to an increase in surface area. Pressure. If I have gases in a piston and I put pressure on the piston so that the gases are compressed, let's assume that these two scenarios are at the same temperature. I have essentially increased the concentration. By increasing the pressure, I have increased the concentration, assuming the same temperature. And so if I've increased the concentration, I'm going to increase the frequency of collisions. Increasing the frequency of collisions will increase the rate. So increasing pressure for gaseous reactions will increase the frequency of collisions by effectively increasing concentration. Therefore, the rate of reaction will increase. And that pretty much is a wrap. We've got a few things to wrap up the video. In terms of connections to other topics, this is the same as 6.1a, really. We'll talk more about activation energy in 16.1. We also talked about activation energy in topic 5 and 15 related to energetics, energy of reaction. Got solutions in stoichiometry, connections there, kinetic molecular theory, and the particle model from topic 1, especially for gaseous reactions. As a summary, by increasing either the frequency of collisions or the percentage of successful collisions, or both, reaction rate can be increased. Temperature, concentration, particle size, aka surface area, pressure, and the presence of catalyst can all be used to affect the rate of a reaction. Now, if you want to summarize more, for example, increase in the temperature increases the rate, and make some statements in that form, that might be helpful for you. Checkpoint question. Here's my question for you. This one asks you about a catalyst from video 6.1a and temperature from this video. Take a look at the question, give me an answer, and then come back to the video. So pause the video and come back for an answer. And the answer is B. Adding a catalyst does not necessarily increase the collision frequency, but it does decrease the activation energy such that a higher percentage of the collisions are successful. Increasing the temperature does actually increase the collision frequency, but increasing the temperature does not change the activation energy. It simply gives more particles an energy higher than the activation energy. Here's another question for you. Copper carbonate reacts with excess acid. Carbon dioxide gas is produced. The curves shown were obtained under different conditions, curve P and curve Q. The change P to Q could be brought about by which of the following? Pause the video, come back for a discussion. Have you paused the video? Come back for the answer? There you go. The correct answer is B, decreasing the mass of copper carbonate. Copper carbonate is a solid reacting with an aqueous acid. So if I decrease the mass, I will decrease the surface area, which would make the rate a little bit slower. And if I decrease the mass, assuming it was the limiting reagent, I will get less product produced. If I were to increase the concentration of the acid, the reaction would go faster, and depending on limiting reagent, it might stop here if the copper carbonate is limiting reagent. If the acid is limiting reagent, then it would go faster and it would make more product. Decreasing the particle size of the copper carbonate. If I decrease the particle size, I'm going to get a faster reaction, but I will end at the same spot. So that is C. And then D, adding a catalyst. Adding a catalyst would make it go faster initially, but it would also finish at the same amount because a catalyst doesn't have more yield. So we have to think about yield here with these type of questions, and we have to think about rate. So yield, of course, goes back to stoichiometry from topic 1. Stoichiometry is everywhere. Thank you for listening. It is much appreciated. Remember, there is a Google form for you to complete. 6.1b. Thank you. Have a great day. I'll see you in class.